Okay, we have an introduction video to section 10.4, polar coordinates and polar graphs. Rectangular coordinates, which you have used in graphing up to this point, are in the form of x, y. Polar coordinates are in the form of r theta. Here's an interesting thing. In the Cartesian plane, the x-coordinate is the independent variable and the y depends on x. So in the polar plane, the independent variable is actually theta, and r is dependent on your theta. So, all right, let us recall from our geometry that the cosine of theta is x over r, so we can solve this for x and get x to be r cosine of theta. The sine of theta is y over r, so y is r sine theta. We also know from our geometry that x squared plus y squared is r squared, so r is the square root of x squared plus y squared. And the easiest way to find our angle when we know x and y is that we know that the tangent of the angle is y over x. So we are going to graph each of these coordinates in the polar plane, 4 and 45. Now, first of all, my radius is 4, my angle is 45 degrees. Here is 45 or pi over 4. I am going to let every two of these represent 1 unit. So 4 along the 45 degree radial direction. So there's 1, 2, 3, 4. Here is point A. B, -4 and 45. Well, -4 means we are going to, along the 45 degree radial arm, we are going to go in the -4 direction. So 45 degrees, but opposite that direction, which would take us this way. There's 1, 2, 3, 4. Here is point B. Now what about point C? 6 and pi over 2. Well, pi over 2 is here, and 6, I don't even have 6 units, so here it is, C. I'm going to go one more past that. And then D, -3 pi over 2. Here's pi over 2. -3 would be on the pi over 2 radius, but in the negative direction, not that direction, this direction. 1, 2, 3. And there is D. Convert 2 5 pi over 6 to rectangular coordinates. So this is the form r theta. We know that x is r cosine theta. So my x is r times the cosine of 5 pi over 6. 5 pi over 6, we are in quadrant 2. The x-coordinate is negative square root of 3 over 2. So this is 2 times negative square root of 3 over 2. So my x-coordinate is negative square root of 3. Y is going to be r sine theta. So that's 2 times the sine of 5 pi over 6. So y is 2 times 1/2. So y is 1. Here's my x, here's my y, and my coordinate pair is negative square root of 3 and 1. Convert 3 square root of 3 to polar coordinates. Well, our r is x squared plus y squared, square root of. So r is the square root of 3 squared plus -3 squared. Notice that radical sign has to go all the way out. So r is 9 plus 9 under the radical. So r is the square root of 18, which that can be written as 9 times 2. So r is 3 square root of 2. There's my r. How am I going to find my theta? My tangent of theta is y over x. So tangent of theta is -3 over 3. So tangent of theta is -1. So that means that theta is the angle whose tangent is -1. The interval for tangent is negative pi over 2 to pi over 2. So we're negative here. That is 7 pi over 4 So I could write this as 3 square roots of 2 for my radius and 7 pi over 4 if I need my theta to be between 0 and 2 pi. Or now we get into other ways to name angles. I could have named this 3 square root of 2 and negative pi over 4, which fits in with our specific interval for arctan. Okay, if you want to write these examples down, go ahead and write the work. So converting to polar form, y is 4. So we know that y is r sine theta. Converting it to polar form is 4 equals r sine theta. That's it. That's all you can do. What about x squared plus y squared is 16? We know that this makes r squared equal to 16. So r is plus or minus 4. Okay, r equals 2 cosine theta, convert to rectangular form. Well, this doesn't follow apparently any of our forms up there, but if I multiplied both sides by r, what I know about r cosine theta is that is going to be x. And what I know about r squared is it is x squared plus y squared. So x squared plus y squared equals 2x. Well, we know how we could make this into rectangular form. Subtract the 2x. I can see I'm going to have a binomial squared plus y squared equals, 0. Interesting. What can I do with that? Well, I can write this as x squared minus 2x plus 1 plus y squared equals, well, if I added 1 to the left side, I have to add 1 to the right side. And we get x minus 1, the quantity squared, plus y squared equals 1. There is my rectangular form. We can see that this is going to be a circle centered at 1, 0 with radius equal to 1. Now, how do I work with letter B? Well, I know here is that I know that the tangent of theta is y over x. So the tangent of 3 pi over 4 is going to be my y over x. Well, that is negative 1, is y over x. So that will give me y equals negative 1 times x. There is my rectangular form. If you wish to write down the work for these two examples, go ahead and do it now. How do we graph r equals 4? This is a circle with radius 4. So 1, 2, 3, 4. I'm going to let this be 4. So it is going to be every point that has a radius of 4 units away from the pole, which is what our origin is, the pole. There you go. There is r equals 4. How do we graph theta equals pi over 3? Well, we know this is pi over 4 here. This one's pi over 6, and this is pi over 3 along this radial arm. And I am going to write this. This right here is theta equals pi over 3. Anything on here. This is negative pi over 3, but it's on the pi over 3 line. It could be anywhere there. Okay, r cosine theta equals 2. Well, what do we know about r cosine theta? We know that r cosine theta is x. So this is x equals 2. It's the line x equals 2. Now, graphing this one, notice that I've got to change my mode into polar form and make sure that you are in radians. I need this to say r equals. So my equation r equals, if I solve this, would be 2 divided by cosine theta, close parentheses. And let's go to our window, and I'm in polar form. Let's see what happens. I want to go one time around the circle. This is graphing it. Last time I think was pi over, might be 24. And I think I can make my window smaller, so it's going to, I'm going to go -8 to 8 and -4 to 4 because my window is 2 to 1 in the ratio of x to y. All right, let's see what happens. There it is. What if I graph r equals 4? Here we go. There is r equals 4. Cool. And finally, r equals 3 sine theta. Okay, this time I'm going to go about this a little bit differently. I'm going to make a chart. Okay, so when theta is 0, r is 3 times the sine of 0. Sine of 0 is 0, so that's 0. So at 0, my radius or distance from the pole is 0. All right, let's try at pi over 6. This is 3 times the sine of pi over 6, which is 3 times 1/2, which is 3/2. All right, so here's my pi over 6 radial arm. 3/2 would be 1.5. So there is 1, here's 2, here's 3, 1.5 is right there. Let's try pi over 4. 3 times the sine of pi over 4, which is 3 times the square root of 2 over 2. All right, that is 3 times about 1.4 over 2. That's 4.2 over 2, about 2.1. Okay, so at pi over 4, I am at 2.1. So there's 1, 2, and a little past it. You know what? Let's see it. Pi over 3, that's 3 times the sine of pi over 3, which is 3 times the square root of 3 over 2, which is 3 times about 1.7 over 2. That's about 5.1. Divide by 2 is about 2.5. So let's make this about 2.6 or so. So on the pi over 3 radial arm, I'm at about 2.6. So there's 1, there's 2. 2.6 is a little farther past it. What about pi over 2? At pi over 2, that's 3 times the sine of pi over 2, which is 3 times 1, which is 3. Now, if you look very carefully, and I connect these in the order that I did them, from 0 to pi over 2, I have a semicircle. Guess what? If I keep going, I'm going to have, at this point, it's going to be about 2.6 on the pi over 3, so there's 2.6. Okay. On the pi over 4, it's going to be about here. On the 5 pi over 6. So at 2 pi over 3, we're going to be also at about 2.6. At 3 pi over 4, we're going to be at about 2.1. And at 5 pi over 6, we're going to be at 1.5, 3/2. And when we get back to pi, sine of pi is 0. So here is, I get a circle. But notice where my circle is. It is centered at 3/2 on the y-axis. If I go to graph this, there it is. Okay. So we can see that if we are looking at r equals 3 sine theta, we are looking at a circle with a diameter of 3 on the pi over 2 radial arm, and it only took from 0 to pi to get there. So if I actually change my equation into a follow the path, let's look at that. Watch this. Follow the bouncing ball. There is 0 to pi, and it's going to do it again. Isn't that neat? Okay, this concludes the first intro video for this section.